In this follow-up class to the concept of vector spaces, we're going to play in class with a number of examples and identifying some new and sometimes surprising vector spaces, sometimes not, maybe some vector spaces which are very familiar to us but not as vector spaces and so on. So what we're going to do, what I'm going to do here is simply point out how do we identify whether a set that we're given is in fact a vector space or not. Well, of course, first of all, what we need to do in order to identify, to verify that a set with two operations of vector space is to make sure it is a set and it has two operations. Okay, so if we don't have one of those two things, then we can't even start. But assuming that we do have a set and that we do have a two operations defined on them, then what do we do next? What we're going to do next is, of course, we have to check that all 10 axioms are satisfied. So remember, we have 10 axioms, whether you use them in the order provided by the textbook or in the order that I provided them to you, it doesn't matter. Still, in order to check that you're dealing with the vector space, you have to check each and every one of them. Okay, so if you can only say for sure, yes, I'm dealing with the vector space once you've checked all of them. Again, this may look like a long procedure, but it's necessary. You cannot get out of it. On the other hand, if you want to verify that a set is not a vector space, and again, we're still assuming we have a set and we have those two operations, all you have to do is check that one of them is not there. So let's say that the number 6 here does not work, then we can tell for sure this is not a vector space. And how do I check that it does not work? It's enough to do that through one counterexample, just to show you that if I can show you that one of the axioms does not work with a specific choice of scalar, vector, two vectors, or whatever it is, then that's enough to destroy the whole building. So it's a very unstable kind of structure, if you want, in the sense that not that the vector space is unstable, but it's unstable to make sure that everything works. Okay, so as long as one little pin doesn't work in there, then the whole matter doesn't work. It's sort of like a very complicated engine. If one of the pieces doesn't work, the whole thing will shut down. So this is a very, very important thing to consider. So don't just check 2 or 3 of the axiom, just random check to see if some of the parts work. Everything has to work, otherwise it will simply crash down and you're not going to have a vector space. One other important thing to notice about vector spaces, and that is the following. Sometimes you may have two vector spaces that actually consist of different vectors and sometimes even different operations. But they may be connected to one another so that the difference is only in the name or the presentation. So in other words, the vectors are named or represented or imagined differently, and the operations are also presented differently, but you can connect them in such a way that they end up being the same thing. Okay? So when this happens, we're going to say that the two vector spaces are isomorphic. So I'm going to use this expression often later on. I'm going to actually, as we move on through the course, I'm going to give you also more specific, more precise definition of what makes two vector spaces isomorphic and how to check it for sure. Okay, but for now, just keep in mind that the basic idea is that we're dealing with two vector spaces where the names or the way we represent the vectors and the operations may be different, but they really correspond to one another very strictly. Okay, so just to give a very basic example, and then we're going to see some more in class. Think of all two-dimensional vectors, right? We've seen that those two-dimensional vectors, or we're going to see it, that they form a vector space. So otherwise, what would we call them vector spaces if vectors are not vector spaces, right? So two-dimensional vectors are vector spaces. But now I can see them differently. I can see each vector as each two-dimensional vector is a 1x2 matrix, right? So I can think of the set of two-dimensional vectors and the set of 1x2 matrices as really the same thing. I'm just thinking of them differently. In this case, actually, is a particularly simple case because even the notation is the same. But again, in substance, they are in a way a little bit different. Okay, but if we use the same operation, the usual operations, then they're really the same thing. And so the set of two-dimensional vectors and the set of 1x2 matrices, we say that they are going to be isomorphic.